Good morning. It's my pleasure to welcome you to the traditional SUSEN conference. This year's conference is already the 7th and is dedicated to materials for nuclear power plants, not only for existing ones, I mean for generation 2 and 3, but also for generation 4 concepts. Materials research is one of the key areas of research at the Research Center Řeš, because within the SUSEN project we managed to build really a large and unique infrastructure which allows us to participate in important international projects within large international consortia. And therefore, I am really glad that our program includes also presentations from our traditional partners, from CMAT, GRC Petten, and University of Birmingham. I would like to thank Jana Kalivodová, who, together with you, prepared a really interesting program, and I pass her the word to manage the program. Jano?
Good morning, everybody. Thank you very much to Tanesh Burket, our Director for Strategy, for the nice introduction of our conference. I welcome all of you here in the hall. And yes, as already been said, we have several international guests, and big pleasure is to say that the first presentation opening of this event will be our honor guest, Marta Serrano from CMAT. She will give the presentation on the project Entente, and she will tell you more about it. But I would like to introduce her. She has more than 25 years of experience in CMAT, in study of degradation of materials, mechanism of under extreme condition. Particularly, she is involved in the determination of the mechanical properties of the materials. Marta is head of Division of Materials of Energy Interest at the Department of Technology. And the division has a recognized position at national and international level. She is the project coordinator of several projects related to materials. She's also participating in OECD NEA working groups. Of course, is a member of the joint program Nuclear Materials, and she's also working in the materials group of Spanish nuclear fission energy technology platform. Last not least, is also an active member of the ISO and ASTM and standardization committees. So, welcome, Marta. Marta is not here, as you could recognize, but she is very kind to give the presentation online. So, I give the floor to her, and please, if you can connect, and yeah. Perfect. Good morning.
Good morning.
And thank you for the presentation.
Okay, and you can see my presentation also, I guess. So I want to thank you for the nice introduction, Jana, and I want also to thank you for inviting me. For me, it's a pleasure to open this conference. I am sorry not to be there, but I have another commitments here in Spain. And again, thank you for the invitation. I have some works on my building, so if sometimes you hear extremely noise, I will try to do my best. So I am going to show you a short presentation about the Entente project. As the title itself said, Entente deals with the design, population, and exploitation of a database of radiation enrichment of reactor pressure vessels. I am the project coordinator, and my work package leader are Julian Sanahuna for EDF, Christian Robertson from CA, and Matti Lindros from BTT. So the problem that we deal in Entente project is the neutron enrichment of the reactor pressure vessel. It's not a new problem. It is very well known that the reactor pressure vessel material becoming brittle during operation due to the neutron irradiation. But we need to take into account that this component, the reactor pressure vessel, is not replaceable. You cannot replace the vessel, okay, at least economically. And it is a large component. And the operating condition, it's around 10 megapascal and around 300 Celsius degrees. And the radiation enrichment is the key point. When we talk about neutron enrichment, we need to take into account that it is a multi-scale phenomenon. That is, the neutron irradiation affect the microstructure, creating defects. And this microstructure-induced defect affect the mechanical properties of the material. That is that when we study neutron enrichment, we need to go from the very basic physics concept through all the microstructural technique, most tensile Charpy test, and also fractal toughness test. To go from this atomistic level to the fractal toughness is a challenge. And we need to understand the atomistic effect to try to understand better the mechanical properties effect. So as I mentioned, this issue of the neutron enrichment of reactor pressure vessel steel has been the topic for several research in the last 5 decades, I can say, and also within European projects. Now, when we start to prepare Entente work, Entente proposal, we start to think about to go a step further. I mean, to start to study the neutron enrichment effect with a modern approach. The approach is called material informatics. That is, you couple in the same loop of analysis microstructural prediction tools, material property prediction tools, processing modeling tools. In that case, we are not going to process in a new vessel, but all this loop, when you link microstructural and material properties, it is based on a data generation and storage tool. If you have not a good database, you cannot apply this new data analysis as artificial intelligence, algorithms, and so on. And it is this data generation and storage tool will help to understand the link between the microstructure and the material property prediction tools. In the case of the reactor pressure vessel, we are obliged to follow a very strict codification and rules for the assessment of the integrity of the vessel. So we are not only playing with microstructural tools or prediction tool. The goal is to follow or to improve even the regulatory scheme for the reactor pressure vessel integrity assessment. So with this idea to start to work in a new way on the neutron enrichment issue, we prepared the Entente proposal. Entente means European Database for Multi-Scale Modeling of Radiation Damage. And the main aims is to design a new European experimental and modeling material database devoted to the understanding of radiation damage of reactor pressure vessel steel. We sent this proposal to the call 2019-2020, and it was approved. We divide the objectives in specific objectives and exploitation objectives, because one of the main objective of the Entente project is to exploit the use of the database. I will go at the end of my presentation to this issue. But the specific objectives are, of course, to design and maintain a unique experimental modeling database for model validation and calibration. This design and maintain is very important. We are not going to kill the database when the project ends. We have a compromise to maintain at CMA the database for 10 years after the project finalization. To collect previous data and enrich the database with microstructural and mechanical data of neutron irradiated RPV steels. We want to focus only on RPV steel and radiation damage. but also to develop advanced model based on data analytics, mining, and previous knowledge. There is a lot, we will see in the next slide, there is a lot of data produced in previous projects that we want to collect and to preserve. And the exploitation objectives are to improve the Soteria platform. The Soteria platform is a multi-scale platform to estimate the radiation damage from the atomistic level to the more or less the fractoctomes level. It has been developed in different previous projects, and we want to improve this platform. We want to encourage the dissemination of results, of course, and foster international collaboration. So the project started in September 2020 and will end in August 2024. In this scheme, I try to summarize all the projects. It's difficult, but I try to do it. In the center, we have, of course, the intended database. To feed the database, we have data of irradiated material, microstructural and mechanical properties, but also models developed in previous projects as perfect, long life, perform 60, Soteria, etc. We have also data from national projects. We want to have a database specifically for RPB steel, so we need to design the software and hardware test protocol. We want to exploit the database with hybrid models using, for example, machine learning. And here on the right, you see all our exploitation objectives: the Soteria platform, international collaboration, and dissemination of results. The consortium is quite large. We are 27 partners for industry, research center, but also small, medium enterprise from 12 countries, including Ukraine and Japan. And the grant is 4 million euros as usually. You can see here all the partners, and you can see also that the budget distribution is more or less similar for everybody except 2 or 3 large people, but the budget is more or less equally distributed. I am going to talk now about the challenge in the creation of a database. When we start to write the proposal, we need to start to learn and to study new concepts that for us, for scientists, I am a mechanical property scientist, are totally far away from our business. And the key challenge is to define the database architecture. And for that, we need to talk about ontologies of data. We need to decide if we want to have a relational database, we want to have interface with other database, and all this work is not done by material expert, it's done by informatic experts that are in the consortium. So we have a partner who is devoted to the design of the database with all these new concepts that are far away from the material business, but they are working on the database, and we will show you some examples. When you talk about data are important, but the most important are the metadata. This means you can see here this iceberg figure here. The data is only 1/3, 1/4 of the information that you give. The most important information is the metadata. In the case when you are talking on irradiated material, the metadata is very important because in the metadata you have all the irradiation conditions, for example, how you the testing protocols and so on. And the data, for example, will be only the tensile results and so on. As I mentioned, we have a compromise here at CMAT to maintain the database for 10 years after the project finalization. Other key challenge is the rescue of all data. There are a lot of data produced in previous projects with neutron irradiated material of high value, and the ideal situation will be to have the same material with the same irradiation condition, to have the computer simulation data, mechanical properties, and microstructure. When you work with irradiated material, it is not always fulfilled, this requirement. It is very rare that in one condition we have the full mechanical properties, the full microstructure, and you have also a computer simulation. But this is the ideal situation, and we want to approach or to go through this direction, to have all the data, all the experiments from one condition. But the problem is that the data is produced with different partners within different agreements. Usually it's stored in personal computer, as all experimentals know. We have some experimental modeling gaps, and the most important here is to stabilize the data pedigree of the data. Other key challenge on the definition of the database is the definition of the formats, data formats. For mechanical property, it's quite easy because mechanical properties are determined following a standard, and in the standard you have more or less defined the format of the report, I say. When we are talking about microstructure and moreover on modeling, we have no data format defined. How we store it at the picture, how we store the results of a Monte Carlo model. So we need to define data format for these activities. And also we want to have interoperability with other material database, because other material database exist. And for example, the European Material Modeling Council has a database, European Material Characterization Council, IAEA has a model database on Cascade, NEA, and so on. So we want also to define the database as interoperability with other material database. In that issue, we have involved NEA people also in the consortium. They are all totally informed about the database effort. So in principle, during these 10 years after the project finalization, we can reach an agreement with NEA to export the database from CMA to the NEA, and there they will be there for longer time. The data collection is also a key challenge because we are scientists. We need to re-educate ourselves. I mean, we need to re-educate ourselves in producing the data and store the data at the same time. It is very difficult. But for that, we are going to define, it has been already done, testing protocols in order to define the data stewardship workflow from the machine or from the experiment to the database directly. So this is the key challenge for the database. I will go very quickly now on the different work that we have already done in Entente work package by work package. We have a central work package that it is the database design, data collection, and so on. We have a work package 3 on generation of new experimental modeling data that will fill the gaps on the material data that I showed previously. And we have a work package 4 that it deals with the accelerated model and new analysis approaches as the ISME approach, artificial network and machine learning, and a hybrid atomistic model. I will go very quickly for here. For work package 2, we are in the infancy of the definition of the database. We know, we know that in 4 years it will be very difficult to have the full database defined. But at least we have do the first step on the data formats. We will see you, data formats committee. We follow the structure of existing database on RPB Steel, Plotter, and REAP. And we want to integrate the database with the Soteria platform. For the data format, we have established data committees of experts that are defining the data format for different techniques. You can see here the different committees that we create for transmission electron microscopy, SEM, atom probe, small angle neutron scattering, positron annihilation, mechanical properties, and you can see here in orange all the data committees for atomistic model, atomistic model, microstructural evolution model, and so on. So all these committees are working. The first one that has already a data format and X structure is the Mechanical Property Committee, as expected, as we have the standardization of the mechanical properties. But I want to say that these two committees are working very well, the Transmission Electron Microscopy and the SEM committee, collecting data and defining data format. So more or less, the Entente database is composed by a high-level part where we define the exposure detail, the neutron irradiation or ion irradiation details. And we have all the information here about the neutron irradiation, the material, specimen, heat treatment, chemical composition, capsule, exposure, and so on. I want to show you the mechanical properties database that it is already defined. We use existing data, MATDB, REAP, national European projects, and ISO and ASTM terminology and definition to define the mechanical properties database. You can see here that some of the mechanical properties are RPB specific, as the drop weight, the T0 determination, and crack arrest toughness. So we use more of the data that already exists, but we include RPB specific mechanical properties. About the Soteria platform, this is only to show you that the Soteria platform is a multi-scale modeling platform, and we want to improve the Soteria platform here with different models and so on. I go quickly. Here is an example of how we proceed when we produce new data in Entente. That means all the data that we are producing in Entente are devoted to be directly transferred to the database. You can see here, when we do EBSD analysis, we will transfer the data directly to Entente database. For the dose rate degradation condition will be transferred directly, and the results will be transferred directly. This is the scheme that we want to follow. Each data that is produced in Entente will be transferred directly to the Entente database. I want to show you some of the new analysis technique from data mining and intelligent artificial algorithms that we are using within Entente. First of all, BTT is defining the workflow for the use of microstructural data and also this is a tensile test, in order to integrate this knowledge on an integrated computational material engineering, the ICME approach, that it is the one that you don't need to have all the information in all the scales. You can go from one scale to another scale, for example, from atomistic model to microstructure by semi-empirical models. Or not all has to be atomistic based or physical based. I want to show you a very nice example on the use of the exploitation of data with artificial intelligence algorithms. The one is the work performed by Nicolas Castain et al. When they demonstrate that a hybrid model, that it is a hybrid model of kinetic Monte Carlo model, this is a pure atomistic model, coupled with artificial intelligence algorithms, can predict quite with high accuracy the enrichment of the reactor pressure vessel, only knowing the chemical composition of the material and the irradiation condition. This is already published, and we use 100 atom probe tomography measurement and more than 1,000 experimental data. This is very, very innovative. We have also another very good result on the use of a new analysis technique. This is a publication from Diego Ferreño et al. And we use the existing database of the RPB enrichment, RPB capsule from Plotter database. Plotter database is the database that supports the ASTM standard on the evaluation of the surveillance program. So there is a Plotter database that includes more or less 2,000 more or less data of Sharpie shifts. And then what we did here is we use the Plotter database and we try to predict the shift using artificial intelligence algorithms. And you can see here the gradient boosting gives less scatter than the usually enrichment trend curve that it is semi-empirical used in the ASTM 900. So this is also a very impressive result that the artificial intelligence algorithms give less uncertainty than the existing enrichment trend curves. With this, I come to the exploitation of the data and exploitation of Entente results. We want to divide or to consider different levels of exploitation. Here on the left, you have the exploitation of the Soteria platform to perform parametric study, very basic science. For example, I change the spectrum and what is the final microstructure. I change the temperature and what is the difference in the microstructural damage. If we go up in the scale, we also want to exploit the Tagnes prediction by local approach to fracture. And if we go to a level, a high level of use, we want to exploit the Entente database to improve the embrittlement trend curve and also to support ASME code case. But also we have identified strong links with other Horizon 2020 projects, Euratom projects that deal with RPV embrittlement. Of course, we have Estromat project and Fractesus project. Estromat, we can use Extromat data. Extromat deal with the variation of nickel, manganese, silicon on the transition temperature shift. We can use this part of the exploitation, I mean the Soteria platform, to analyze the microstructural evolution. In Fractesus, they deal with the determination of fracture toughness or irradiated material, but also can be supported by fracture models. And if we go up, and we go in an engineering level, the embrittlement trend curve, we have here identify several international collaboration, but also Fractesus and Estromat, where they are producing fracture toughness data can be also stored in the Entente database. We have already defined references cases to exploit the data. The first one has been defined by Framatome, Germany, and it is a sample problem to support the technical basis of the new ASME code case on the use of the master curve. I am not going to enter into detail, but the reference case participant, we will ask to calculate the shift using the Entente database to provide individual values of this input. And this will be used to support two ASME code case on the use of the master curve. We have defined another reference case. It has been defined by Mark Kirk. And then the problem here is new scale, small modular reactor. The problem of the new scale vessel is that the material has higher manganese, higher nickel, and low irradiation temperature. You can see here in this plot. This is the irradiation condition for new scale. The temperature is extremely low, lower than the existing RPV steel, RPV in operation, but also the nickel content and the manganese content is extremely high. We are going to set up a reference case. It has been already set up with this chemical composition and this irradiation condition, and try to use this hybrid model with kinetic Monte Carlo and artificial intelligence to estimate the shift, the transition temperature shift. And with this, I reached the end of the presentation. Entente started in September 2020. We are now in month, reaching month 24. The specification of the Entente database is available. The database will be populated along the project execution. Next year, we plan to start to populate the data with the database with the data that has been collected. The first experimental results are available, and the first analysis with machine learning are available. And with this, I end the presentation. I guess you can hear me beside the works I have just on my window, but I am sorry for that. I am ready for questions if you have any.
Marta, very much for your presentation. Thanks a lot for nice opening. And if we have some question here in the plot, I'm happy to bring you a microphone and you can ask Marta, since we have her here at least a long distance, what you are interested in. So, any question? Okay, Marta. It seems that Yeah, it's early morning.
I will be here at least up to lunch, I think.
Yeah. So in this moment, there are no questions. Thank you very much one more for your presentation. I think we can applaud you if you can hear us. So thanks a lot.
Thank you.
And yeah.
Thank you, Jana.
We can move to the next presentation, which is going to be from CVR, and it's our also female presenter, Petra Gavelová. She will tell you something about the CVR infrastructure for the study of nuclear fuel cladding tubes, including accident-tolerant fuel. So I try to. Já jsem se měla.
So good morning, ladies and gentlemen. I'm Petra Gavelová from Research Center Rzesz, from Material Analysis Department, and I will introduce you our CVR infrastructure for complex studying of nuclear fuel claddings, including accident-tolerant fuel claddings. So I will introduce a little bit zirconium-based cladding topics at the beginning. Then I will tell you some of our CVR activities in nuclear fuel cladding, including ATFs. Then I will introduce you the nuclear fuel inspection activities in a CVR, which is led by my colleague Marcin Kopec. Then I will switch to the mechanical testing of neutron irradiated cladding tubes in shielded hot cells, which is led by my colleague Alica Federikova. And the last of my point will be the part of microstructural analysis, which is focused on electron microscopy studies, mostly on scanning and transmission electron microscopy, which is led by my colleague Patricia Holodová. So, what are the zirconium-based cladding tubes? Let's say that this is the ultra-pure zirconium with alloying elements of niobium, tin, iron, and chromium, and they have very good properties for cladding tube applications, mostly because of their neutron transparency and good corrosion resistance to withstand the extreme conditions of the primary reactor circuit. The materials, the zirconium-based cladding have a very high ductility and strength. So the combination of these properties gives them then importance in nuclear to be nuclear cladding tubes. What happened under normal nuclear power plants operating conditions and long-term storage? During the process, there is the interaction of the claddings with the neutrons. So the radiation-induced defects are creating in the microstructure, and they causes the degradation of mechanical properties. So that means the material is hardened and embrittled. We can observe the radiation cream. It means the volume changes due to the anisotropy of zirconium alloys. And we can observe as well the oxidation reactions of the zirconiums with cooling water, and we can observe the hydrogen diffusion into the matrix by analysis of hydrides in the microstructures. Briefly about the accident-tolerant cladding concept, which studying speeded up after Fukushima in 2011, and ATF cladding concept tell us the improvement or replacement of currently used zirconium-based cladding. So we can speak about the ATF cladding materials or ATF fuels. ATF cladding materials try to modify the current cladding materials, so by coated zirconium alloys or improved zirconium alloys. And from advanced materials, we have some advanced steel refractory metals and silicon carbide ceramics. From the perspective materials, we can mention the chromium-coated zirconium alloys, which are tested in nuclear power plants from 2019. As well, very perspective materials is so-called FICRAL, so it's iron, chromium, and aluminum-based metal, and widely tested is silicon carbide materials from the ATF cladding materials. From the ATF fuels, there is the way to improve uranium oxide material to develop the high density fuel and encapsulated fuel. Something about our activities, which are focused mainly on neutron irradiated materials. As I mentioned, we have the group of nuclear fuel inspection, which is a huge support of Czech nuclear power plants. We have the huge area of perspective methods, debris threatening testing. We have a lot of projects concerning radiation induced damage evaluation of different kinds of zirconium alloys. There is the project of irradiation in nuclear power plant Temelín from 1 to 6 years, and then we do mechanical testing and microstructure analysis depending on a neutron fluence. So we evaluate the effect of neutron fluence on the microstructure. Then we study irradiation growth of different types of E635 alloys. So it's a Russian alloy which is irradiated in LVR-15 reactor in Rzesz. And we study the in-pile creep of E110, optimized zero, and as well ATF claddings, which are based on chromium and chromium nitride coating. So these materials are as well irradiated in LVR-15. And as well, the huge area of the study of zirconium alloys is a high temperature oxidation as well of different zirconium alloys and ATFs with the cooperation with UJP Institute in Prague. So going to the nuclear fuel inspections, which support the Czech nuclear power plants, we provide NDT methods. CVR developed the ultrasonic system for fuel assembly geometric measurements. This system automatically detects the spacer grids on the fuel assembly and conducts the measurements in this area. Here is the example the output of ultrasonic system application the real fuel, which is the single site measurement, and there the system automatically detects the space grids which are marked by a DM. CVR as well developed the automatic digital image processing for fuel inspections optimization and enhancing the speed and accuracy. It eliminates the human factor, and digital image processing helps also in on-cladding changes like oxides, hydrides or pitting, which we can notice on the fuel rods. Going to the very perspective method of debris threatening testing, which is performed under our fuel group. Debris threatening testings we can perform in air conditions at room temperature, in wet conditions, in defined chemistry, as well as elevated temperatures, and as well we can simulate in the autoclave the as-real conditions, PVR, BVR, and VVR conditions. So here are some results from the debris threatening testings where we compared two types of ATF claddings, and there is visible the threatening depth of different coatings as well supporting by the microstructure where we can compare the results on the surface damage. Our field group as well do the oxide layer measurement by electric current. So the electric current oxide layer measurements in wet conditions we can see compared to the standard weight gain methods, and there is perfectly visible the cloud type of the oxide in crease with almost no water intake. And as well we do neutron radiography. This is as well the NDT technique to have insight into the internals of the specimen. So mainly that was developed for hydrogen aggregation assessment with the precision on the level from 12 to 16 ppm. Going to our second group in our department, which is mechanical testing group of neutron irradiated cladding tubes in hot cells. So we do the standard mechanical testing as well. We develop the new methodologies mainly for evaluation of ATF claddings. So we do tensile compression, bending testing, high temperature creep, low or high cycle fatigue. As well we do micro and nano indentation and adhesion testing of claddings and ATFs. And we have in hot cells the autoclave for stress corrosion cracking initiation in the PVR conditions simulated. So here is the insight to the hot cells, and there are the example of specimens after tensile testing in axial and transverse direction, which we perform on cladding cubes. So just briefly what we do, this is the project of testing of irradiated E110, which was irradiated from 1 to 6 years in Temelín. And then we do the mechanical testing like tensile and creep testing supported by electron microscopy to evaluate the radiation-induced damage. I will tell later. And we cooperate with our UJV, within the UJV group, which we compare the experimental data with the simulations. So they predict the mechanical behavior, and we cooperate with our experimental data. Regarding the testing of ATF claddings, we developed within the few projects the new methodology. So we do on ATFs the low cycle fatigue. We characterize the ATF coatings by nano hardness and SEM by wave dispersive spectroscopy. So we notice the chemical changes and local mechanical changes in the ATF coatings after neutron irradiation. And as well, we study some unfavorable effects in fuel claddings and their impact on the fuel safety. So here is the several new methods we developed under the TACHE project. And going to the microstructural support, which is focused on electron microscopy studies, we this is like the last part of evaluation. So we compare the reference and neutron irradiated microstructure analysis and evaluate the radiation-induced defects and structural phases, and as well the radiation growth, and it correlates with the results from the mechanical testing. We as well compare the non-deformed and deformed specimens so that we notice the areas of localized deformation, and these areas are the source of information. There we study the deformation mechanisms. We evaluate the general and local microstructure by electron microscopy methods. Here's the example of tensile testing in axial and transverse direction from the cladding cube. So here's the workflow, how to prepare the specimen from the transverse sample. From the transverse direction of after mechanical testing. So we choose the place and do the cutting, grinding and polishing to obtain the final tin foil to observe the radiation-induced damage in transmission electron microscope. So it's these irradiated materials are prepared in hot cells and globe boxes. What what we do by electron microscopy, we do image and diffraction analysis and chemical analysis, and then the results from transmission electron microscopy are completed by scanning electron microscopy, where we perform the crystallographic analysis and grain size texture, and we observe the local misorientation after irradiation, and as well the chemical analysis we do in low magnification to complete the TM results. And here are some examples of reference materials, zirconium-based claddings. Are the Russian E110, E635, and E125 microstructure, and as well there are the zircaloy, zirlo, and zero optimized different microstructures. Regarding post-irradiation examination, what we evaluate in neutron irradiated materials, we observe the radiation-induced precipitates and different dislocation loops of A and C types. We can observe the hydrides in the microstructure, and we observe the amorphization of previous secondary part precipitates, which are visible after high neutron fluence. And as well, from the deformed specimens, we describe the deformation mechanisms, which is widely studied. So here are some examples of A dislocation loops in microstructures which are formed at low fluences. This is the first image. The second image, there we can observe the C dislocation type loops which are formed as fluence raises. And then we can observe at the high magnifications the irradiation-induced precipitates associated with these loops. And as I told about the radiation growth of the fuel rods, this C type of loops are responsible for radiation growth. So that's the way we evaluate after different neutron fluences compared to the mechanical properties and the radiation growth evaluation. And these are the images of the place which is marked on the specimen. So this is the specimen taken from the deformed place directly, and we can observe the deformation bands within the grains in the prismatic planes of hexagonal lattice of zirconium alloys. So here we can study in detail, and there is the way that loops might get annihilated or dragged by dislocations, and they produce a clear zone free of these defects. So these free channels serve as a path for dislocation grinding. So this is the strain localization at the grain scale. Here is some results from electron backscatter diffraction that we can complete the TM results in lower magnification. So we can observe the grain orientation and as well the grain texture, and the right image, which the blue one, is full of the local misorientation areas. So we can evaluate the density of dislocations which can be caused by neutron irradiation. So this is the local misorientation method, which we complete the TM results where we observe the dislocations in high magnification. So going to some results from ATF claddings, where we can do the cross-section analysis using focused ion beam. Here is the workflow to prepare the TM lamella, which we do within the SEM chamber, and then we do the chemical analysis and electron backscatter diffraction of chromium and chromium nitride coated specimens. What we as well evaluate on ATF claddings is our ATF claddings after high temperature oxidation, where we developed the method of chemical profiles and the nano indentation profiles which we compared. and there is the chemical change correlated with local mechanical properties. So from this data, we can evaluate the phase changes in reference as well as irradiated materials. So here are the profiles of the chemical and local mechanical changes. So if I will get some brief summary of our research on zirconium claddings, we do non-destructive testing as well as destructive testing, and when we evaluate the influence of neutron and gamma radiation, corrosion environment, heat treatment and deformation hardening, and we do the mechanical testing and we observe the change in mechanical testing, and then we research the microstructure and microchemical changes based and incorporate with the mechanical testing group. So, and then we compare the reference and exposed material. So this is our experimental support of the company. And I would like to thank for your attention, if you have some questions. I think there was quite a lot of information, but just a brief overview of our activity.
Thank you very much, Petra, for your detailed presentation about the inspection of the fuel and testing of the cladding materials, which is actually the first barrier for the fuel going out of the reactor. So very important to have such a developed methods, and I'm really very proud of your team and all the researchers here in CVR that they are actually able to perform such analysis and be a very good player in this area also for chess. So, is there any question? Yeah.
Thank you, Petra, for a very nice presentation. I have just a simple question. What's the lifetime of fuel cladding? How long it can be used?
There is the 40 years, and it should be like lifetime of fuel claddings.
Fuel claddings, yeah. I mean, how long they can be used? You spoke that you irradiate the samples for from 1 up to 6 years. Mm-hmm. So, and I know that the campaign takes like 18 months usually. And so I don't know how long it can be used. I mean, after 18 months, they are reshuffling, refueling, something like that. But I don't know how long they can be used. Just this is the question.
This is it depends on the cladding type, but it's for I guess a few years.
Few years. Okay, that's all. Thank you.
Thank you. Is there any other question for Petra and for her team, for methods which are exploring the fuel cladding, but also other materials, which we will hear later? So, no one. We also connected our stream and sending the conference online, so we have some viewers already, but no question here. So I think that even though that we have still some time, we can move to next presentation and leave the discussion towards the coffee break, because we organized this conference in 3 blocks, and the first block is devoted to the characterization and methods of testing of the material. So we will hear now about non-destructive testing at nuclear power plants from In the end, we have the change of the presenter because of the team has another activity today. So they will be presenting Mr. Jaroslav Brom. So,
good morning, ladies and gentlemen. My name is Jaroslav Brom, and I will present activities of diagnostics and qualification department in the area of non-destructive testing at nuclear power plants. In the presentation, I will speak about our activities related to inspections. I will speak about high temperature ultrasonic testing, 3D scanning and usage of replicas, 3D modeling, development of diagnostic equipment, I mean manipulators, and then I will speak about new methods developed for inspections in our department, about so-called NEWS, nonlinear elastic wave spectroscopy, and about usage of magnetic memory of material. Let me start with high temperature phase array ultrasonic testing. We had two projects. The first one was from 2019 till 2020. Our partner was chess, nuclear division. The goals of the project were to demonstrate the detectability of EDM type defects with defined dimensions, I mean length and height. And the second goal was sizing of these EDM type defects at high temperatures. It was done, or evaluation was done by comparison between room temperature measurements with measurements at temperatures from 100 to 350 degrees of centigrade. What equipment we were using? We bought equipment from Eclipse company from Canada. We have cooled wedges, and also we are using coupling medium for temperatures up to 350 degrees of centigrade. What were development steps? First, we manufactured special gauges and perform measurements of these gauges. Gauges were from carbon steel and stainless steel, the number of materials you can see on the slide. Then we performed the second step. We verified the effect of temperature on the change in speed and propagation of ultrasonic waves on test pieces. In this step, we had homogeneous weld joints from carbon steel and stainless steel, and also we had decimeter weld. The last step was sizing of EDM notches, and as I have already said, we compared results from room temperature with temperatures up to 350 degrees of centigrade. Here I have some slides from these measurements. On the left figure you can see gauges and also cooled wedges with sensors. In the middle you can see how we performed heating. We were using heater clothes covered by insulation. And on the right figure you can see special developed equipment for heating of tube test pieces. We verified this concept. We performed ultrasound measurement and On this picture, you can see the results for, as an example, for carbon steel. On the left side, there are examples of detected EDM notches at room temperature. On the right bottom figures, you can see that there are still detectable EDM notches. And also sizing was okay from the point of view of ultrasonic testing. What concerns of stainless steel measurements, we approved that we can go up to, with detectability up to 300, not 350, but 300 degrees of centigrade. The second project was in 2021. We discussed with the chairs to certify inspections for concrete pipelines in secondary site of nuclear power plant Temelín. We agreed that this qualification should be only on carbon steel materials, which you can see on the slide. We had two different widths of the pipelines, and the process was similar to the process which I presented. In this case, as I said, was creation and certification of inspection procedures. Certificate body was from chess. Here are similar results which you could see for temperatures up to 350, detectability and sizing was okay, and nowadays we have two qualified inspection procedures, and we are in the state of preparation, demonstration of measurement in situ. So it means in technology of secondary site of Temelín NPP. Now let me speak about 3D scanning. We started 3D scanning of seal surface on a reactor pressure vessel main dividing plane. We started first at Temelín, then because we were successful, we were asked to perform similar measurements in Dukovany NPP. On the picture, on the photos, you can see dividing plane in Temelín NPP, and here you can see that we are using 3D scanning arm. 3D scanning arm. We must be careful because we are in radiation area. And you can also see that colleagues, sometimes also me, we had to use Tyvek, so it was not, let's say, friendly condition for operators, for us. Here on the left bottom, you can see the results. There is some wear of the groove. Geometry, and our measurements or outputs of our measurements are used for a lifetime of this part of reactor pressure vessel. Another example is from scanning of sealing for main coolant circulation pump. In this case, operator people from technical inspection, they have information for timely complaint of defective supplies before they are used in technology. This example is again from Temelín. We measure carbon tubes 16 times 4 millimeters inside steam generator. The reason is it can occur corrosion pits on these tubes, and if the event of a leak, then coolant of the primary circuit may leak into the secondary circuit. That's why we are measuring again in this not friendly conditions, radiation, and in this case also temperature from 40 to 50 degrees of centigrade. Here is example from Dukovany. We are asked to perform scanning of super-emergency nozzle of steam generator at Dukovany NPP. The reason of this was mainly for chess, because at the time they were preparing documentation for so-called weld overlays. I will speak about it later because we were producing a manipulator for inspections of weld overlay. Here is an example when we were using replicas for more than 30 years operation. Operator has to open these flanges, and we are asked to perform 3D scanning. We made decision that the best way would be to take replicas and then scan these replicas. And here you can see our results. On the left photo you can see our special tool to take replicas. And now let me speak about manipulators. The first manipulator is so-called Horimir. My colleagues, they take the name of the manipulator from the list of names, Czech names, when we released this manipulator. So this manipulator was released at the date when Horimir has the name celebration. And this special manipulator was developed for inspection of concrete, shielding of reactor pressure vessel at Dukovany NPP. Here are ultrasonic testing for, I have already mentioned, news technology. Here is manipulator for control road nozzle well joints of reactor cover of the Dukovany NPP. Here you can see main features of this manipulator. This manipulator is lightweight and durable and has durable construction. There is electromagnetic pressure of the body, adjustable probe pressure, and so on and so on. Nowadays, chess will start inspections with usage of this manipulator. Here is an example of manipulator which is is currently being developed for measuring of keys and grooves of VVR 440 Richter pressure vessel and core barrel at Dukovany nuclear power plant. In this presentation, we are developing two technologies. The first one is 3D scanning using GoPro camera system. And the second one is measuring by taking replicas with their subsequent 3D scanning. And in this presentation, I will speak about the second one, so about manipulator for remote replicas taking. On this photo, you can see shielding cylinder, and within this shielding cylinder, there is a core barrel with grooves, and this core barrel will be on the crane. There is also a window which will be opened, and behind this window there will be grooves of core barrel. And what we developed, this window during the time of measurement will be close to the floor. So we will stand as developed so-called fixing table. On this fixing table there will be manipulator which will have 3 axis motions in X, Y, Z axis, and then there will be we say a replicator part of the whole manipulator concept. As I have already mentioned, the core barrel will be suspended on a crane, so it was necessary to solve core barrel movement via floating storage of the replicator from the other parts of manipulator. The attachment to the core barrel is solved using suction cups, which you can see here. The concept of pressure jaws was chosen for taking replicas. So the jaws are here, and the first one here, the second one here. We also had to develop special jaw seal, and measuring the width of the grooves is realized by measuring the opening of the jaws using a linear encoder. And again, radiation is too high to stay in front of the window of shielding cylinder. So everything will be done remotely, 30-40 meters from this fixing table. This is a project which that will end next year in June 2023. Here is example what we developed for chess. They had a manipulator, and we developed a remote control hand. So now they will have equipment for foreign object search and retrieval. Here is description of this manipulator. And now let me speak about wet overlay manipulator. I showed you that we scanned this nozzle before just applied wet overlay. Wet overlay is applied on, or will be applied on all super emergency nozzles. During the operation, CHESM has to perform inspections, and we were asked to develop a special manipulator. This manipulator you can see on this figure. There is dimensional limitations which we have to solve. There is self-supporting fixing on the pipe, and that's it. Here are another drawings of this manipulator. In the last part of my presentation, I will speak about new methods. Let me start with the so-called NEWS method, non-linear elastic wave spectroscopy. There are two techniques, and in this case, for pipelines, we use non-linear wave modulation spectroscopy. The principle is that we send two frequencies. We are using two sensors, and one receiver, and we check if there is some frequencies and multiplies of these F1 and F2 frequencies in the spectra. If there are many of these frequencies there, then we can say that there is some nonlinearity caused by a crack. During our research and development, we manufactured special half-tube specimens and perform measurement without and with a cyclic fatigue crack. Then we developed, we call it spectrogram news. We from the spectra we take all frequencies which are multiplication of F1 and F2, but here we put amplitudes only from F1 frequency, and we evaluated that if there is a crack, then we can see in multiplies from 33 to 37, and that's how we can detect cracks. And why we are doing it? At Temelin nuclear power plant, they have leak monitoring of pipe system using more than 100 ultrasonic sensors. Our research and development was on the same sensors which they use in this system. These sensors you can see here. So two senders and one receiver. We also performed evaluation if sensors and pipelines can be used for this method, and last year and this year we approved that this system can be used on Unit 2, not at Unit 1. At Unit 1 they have different hardware, and the signal is 100 times lower value than on Unit 2. The last what I present is usage of so-called magnetic memory of material method. This is passive method of measuring of intensity of the magnetic field, HP, or gradient, depending on distance traveled. We were using equipment from Russia. On the figure you can see typical drawing of magnetogram. So here you can see scanning device. Here I put example from testing of dissimilar metal weld with a crack in this area found via this LAUT method. And we had, in this case, 8 traces. And on trace number 1 and 8, you can see there is a peak of gradient of intensity of magnetic field. So, this was in the area between trace 1 and 8. So in this way, we evaluated that this method can be used for detection of cracks. New method, new usage of magnetic memory of material was tested on a flange. We proved that with this method we can detect loose bolts either with pressure inside or no pressure inside this flange, and also we proved that we can detect over-tightened flange joint bolt. On this figure was loose bolt number 8, and you can see changes on the closed bolts number 7 and 9. So that's the technique how loose bolts can be detected. So that's all, and thank you for your attention.
For the presentation, the last in this block of methods of testing, very interesting. Okay, thank you for your presentation. In this area of testing of the materials, the first part of our conference. And yes, this non-destructive testing in general is a very useful method to predict the failure. And yeah, it's also very difficult discipline to verify and standardize. And I think our team of researchers is doing a very good job. And I would like to ask if there is any question for Jaroslav and the team of non-destructive analysis methods.
No questions, thank you.
Any question? Probably that there were a lot of information and people are still processing. Thank you very much for your presentation. One more. Now we have foreseen a break, but I guess now I don't see if Marta is still there. We could wrap up this part. I see that Marta is connected, so if somebody, for example, was thinking during the time, if you have any question for Marta Serrano or Petra Gavelova or Jaroslav, please, you can ask now, and yeah, we can discuss a little bit. If not, I had a question for Marta if she is still there, but I am not sure, Marta, if you can hear us.
I am here,
or
yes.
Maybe.
Yes.
Yeah.
Hello, yes, could you hear me?
Yeah, we can hear you, perfect.
Okay.
I was wondering, because I am myself involved in some databases and handbooks and so on, if the database from the Entente, since it's the European project, is going to be accessible for, let's say, European community of researcher, or how it's going to be? Because there are a lot of data which probably, not probably, but involving irradiation modeling, testing, a lot of money. So is it going to be accessible, or how is it going to be handled this?
Yeah, the database is designed with an open access area and with a restricted area. The open access, when we will decide which part is open or not, it will be done by the end of the project in 2024. We will analyze all the data and we will decide in the General Assembly which part of the data are open. As you know, the European requirement is that we must open all the data that we can. So in principle, the database open area will be large, but I cannot tell you how large or not.
Okay, thank you very much. I think it's very positive news also for us and for further study of the reactor pressure vessel. Not only degradation, but also development of new reactor pressure vessel, what is foreseen, like 3D printing, additive manufacturing, the all-in-one. So it will be important to know how it influences the irradiation, degradation, mechanical properties, and so on. So it's important to know the history and all the data already gathered until now. So thank you very much. I still look a little bit if somebody is going to use the opportunity and have any question for our three presenters this morning. Some discussion going on, but no hands. Marta, thank you very much, and thanks very much to all presenters. And now we will have a short coffee break, and we will restart according to the schedule later. So thank you very much. So I would like to ask you for the attention. We are starting the second block of our conference, which is devoted to material degradation in different media. And we have the big pleasure to welcome here Radek Novotný. Radek is currently working at GRC pattern. Already from 2003, actually we were starting there the same year. A lot of nice years of experience and different events, not only scientific. So Radek completed his PhD at the University of Chemistry in Prague. And he is responsible for Amalia Laboratory, which is primarily focused on corrosion and environmentally assisted cracking research for current LVR's reactor and future supercritical water reactor. And also the topic of the supercritical water reactor and materials research will be topic of his presentation. So Radek, welcome. Thank you for your presentation, for presenting. And yeah, floor is yours.
Okay, I will try to connect my screen. I hope you will. Can you hear it? Can you see it? Can you see the presentation?
Yes.
Okay. Thank you, Anna, for very nice. So I will start with my talk. Thanks, Anna, for very nice invitation. It's a big opportunity for me. I'm very happy to do it. First of all, I would like to acknowledge David Guzonas, because this was the closest co-worker for many, many years. And then I will start my talk with the topic of status of material research for SCWR. I will first start with the question, why supercritical water-cooled reactor? Then a little bit of historical excursion to 50s, 60s, and the renewed interest in 90s. I will try to describe main features of SCWR. I will talk about the core and plan concepts which were elaborated either within national programs or within European projects or within GIF. And then I will mention project HPLWR phase 2 in particular and related material R&D, just to demonstrate what kind of problems we are facing. And then later on, I will, in the later stage of the talk, I will talk about what are the design challenges, but not the designer's challenges, but more like material expert challenges towards the design. So what we will have to fulfill to little bit make the designers happy. And then at the end, some future plans. So I will start with the question, why SCWR? Okay, because it makes sense to me and many people in the past and in the current, because it's actually merging of two proven advanced technologies of nuclear and fossil fuel power plants. Of course, many utilities in fact operate both nuclear and supercritical fossil plants. And of course, there are more than 430 operable nuclear reactors around the world and more than 400 supercritical boilers around the world. So we have many years of design and operating experience. If you look at a little bit, if you look at into the past, then all started in the 50s and 60s. The first concepts were prepared, developed, but none of them was ever built. But what has been built in the 1560s, it was experimental nuclear power plants with superheated steam. So we don't have any experience from the past with supercritical water-cooled reactors, but we have some experience with superheated steam cooled reactors. If you look at the renewed interest in 1990s, the main driving force was the combat to climate change. And of course, reduction of greenhouse gas emissions. And again, at the same time, big development in developing countries. So it kind of raised demand of stable energy supply. Concepts which were under preparation showed quite high potential for cost reduction. First of all, due to full cost was lower, and second, because of the simplification of the whole plant and using the direct cycle. Then, of course, we could use advanced engine boiler technology, in particular with the development of ultra supercritical boilers and related material research. And then, in combining all these factors, when in the 90s, Generation 4 International Forum was set up, and signatories agreed to pursue 6 concepts. Then supercritical water-cooled reactor was one of them, and 5 countries decided to pursue this concept and work together on development of the concepts. Following that, the concepts were either pressure tube type or pressure vessel type. So that means always using, evolving from the current fleet of nuclear reactors, either PWR, BWR, or CANDU. And then, of course, because of the similarities of the both concepts, it was a big opportunity to collaborate. If we talk about SCWR main features, then of course we need to start with high efficiency because of due to high supercritical pressure and temperature at the core outlet. On the right side, in the bottom part, you can see PT diagram. It shows how much higher SCWR is compared to PWRs. Water is entering the core at 280 degrees C, still subcritical, and then changing up to 500 and leaving the core at 500 degrees C supercritical water. So considerable increase, significant increases efficiency. And of course, simplification of the plant components and layout due to direct cycle, that was another big driving force. And design flexibility. Supercritical water-cooled can be either used thermal spectrum or fast spectrum. It can use advanced fuel cycle and of course uranium fuel as well. And there is also some opportunities for cogenerations. But if we look at a little bit at the problems, then of course we have a look. Big problem is the change of water properties crossing the supercritical point. You can see most of the physicochemical properties is changing significantly when we are going from subcritical to supercritical water. But I would specifically mention specific heat having a peak around critical point, and this is causing effect called heat transfer thermal deterioration, and hotspots according to along the peak leading, and big problems for materials experts, and actually kind of critical part of the development of materials. If you look at the available concepts, I will mention 3 of them. All 3 were developed within GIF and national programs. Pressure tube concept was developed by Canada. European concept HPLWR is the thermal neutron core developed within HPLWR phase 2 project, and we have also example of Japanese example of the fast spectrum, which is, for example, the Japanese fast spectrum SCWR core. If we kind of summarize works on these on the concepts, Canada, EU, and Japan have completed the development of their concepts. International experts reviewed the concept and assessed their viability, and China already completed their concepts as well, but international experiment didn't review it yet because of the COVID-19 situation in China. Russian Federation still working on their concept. If you look at the European HPLWR supercritical water-cooled reactor, we can see the parameters of it in this table. It's a pressure vessel type, thermal neutron spectrum, 25 megapascal water pressure. Water is entering the core at 280 degrees C as subcritical and leaving the core at 500 degrees C as supercritical. It's a 2,300 megawatt thermal power reactor with foreseen efficiency 43.5%, using uranium fuel, and water is working both as moderator and coolant. Water is passing 3 times before it leaves at 500 degrees C, before it leaves the core at 500 degrees C, supercritical water. I will also mention material R&D within HPLWR phase 2, and the reason for this is because it was a little bit of failure. We didn't succeed to identify the material for the fuel cladding. None of the materials passed all the criteria we actually determined before the project as a criteria of success. And the main problem for that was the pre-cladding temperature due to deteriorated heat transfer, which was much higher than 620 degrees C, and we didn't find the material which would have enough strength or enough mechanical properties at this temperature and with the geometries which were used for HPLWR concept. I should also mention supercritical loop, which was designed and built by UGV. And I'm mentioning from one reason, because it's probably the most advanced testing facility we have at the moment in the community, because this is using very high flow rates. First of all, it's the only device we could use in cores for radiation studies, and second it's actually the closest we could get to the real flow rates in the real plant, because it's using very high flow rates up to 200 kilograms per hour of water. Flow rate is possible with this device. So far, the device has never been used in the core, but it was used in outpower test, and it's still most powerful facility we have in possession. If we look at then after the HPLWR phase 2 project, the activities continued, in particular on the development of all prospective materials for the most critical components of the plant. The work continued with the GIF, national programs, and etc. Here you can see that we finally identified most prospective materials. For nuclear fuel cladding material, it's 310S, which is originally used in fossil-fired L100H and L100H. And of course, for reactor internals, for pressure vessel steel and primary steam piping, we could use the experience from current nuclear reactors and supercritical boilers, which made our life much easier. We can use the materials which are used in light water reactors. And for the primary steam piping, P99, which is very well known from supercritical boilers. If you look at the scheme of the plant, then of the whole plant, then from all the materials, and we look at it from the materials perspective, then the only red part on the left side, which is reactor core, needs a significant R&D, maybe even development of the new materials. All the other parts are well known, And like high temperature turbines, this can be used from supercritical fossil-fired power plants. Also feed train, we could use the experience from boiling water reactors and use their system of water purification and so on. If you look at the selection of materials, what has been done for these critical components, from corrosion point of view and from another degradation mechanism point of view, these were identified, the most critical ones when identified, and kind of classification has been done. But please don't take it as a kind of complete classification. Even if you look at the corrosion, which seems to be pretty much solved issue, but in reality it's not. We just, it's more or less gathered knowledge in past 20, 30 years we have. And from that, we a little bit optimistically said that we have some corrosion resistant materials, but we didn't evaluate all the materials which are commented later. In reality, we don't have any alloy at the moment which would fulfill all these criteria, and we have real gaps like in stress corrosion cracking testing, irradiation assisted static cracking, and so on. I will comment later on this. If you look at the design criteria, then of course one of the things which were defined in the HPLWR phase 2 project, it was the performance criteria, which was defined as the total metal loss at the end of service life, and then it was defined like 140 micrometers after 20,000 hours of of service life. And at the moment, and service life. Another parameters which is important, of course, this is the alloy composition. When we know that there are certain limits due to, for example, neutronics. And then, of course, there are key parameters of water chemistry in relation to corrosion, stress corrosion cracking in particular, which needs to be taken into account. And we don't have still enough knowledge to be 100% sure about the selection of materials. And I will comment now in examples on all of these. If you look at the alloy selection, so we perfectly know that ferritic martensitic steels or ferritic steels are much less resistant to supercritical water, even at high temperatures. This is due to lower chromium content compared to austenitic stainless steel. Even the ODS version didn't introduce much more beneficial effect for this. If you look at the results in the upper part, most of the tests we have been doing are corrosion tests. That means we are exposing specimens in the autoclave. We weigh them before and after the exposure, and then we calculate what is the weight gain due to oxidation. Very simple test, but it seems. But when we compare different results for different labs, we realize how big differences we have and how much we must work on improving the interrelation of these labs. Anyway, austenitic stainless steel much better. Many steels, or there are more steels which show very good corrosion resistance even at high temperature supercritical water. I would show one example, which is alloy handle, which is HR3C, which is Chinese equivalent of 310 stainless steel, which shows very low corrosion resistance because of the high chromium content. Again, the research also focuses on ODS because of their potential for good mechanical properties, but at the moment it doesn't show very big benefit in terms of corrosion rate. If you look at the oxide layer, very homogeneous uniform oxide layer, even at high temperature supercritical water. And on top of it, these alloys also showed acceptable mechanical properties up to 650 degrees C supercritical water. But here we, as I mentioned, here we have definitely a gap, because first of all, most of the exposures are short. So it's in the range of 1,000, maximum 2,000 hours. We need longer exposures to extrapolate results to 20,000 hours of in-service life. Second of all, we have we have to concentrate also mechanical properties, and in particular nickel content, because 310S stainless steel and 800H are perspective materials, but they have quite high nickel, and high concentration of nickel is not very beneficial for reactor physics, for neutronics, and also for radiation protection in the future plan. Another challenge or another gap I would like to mention is surface finish. We know that surface finish has beneficial effect for corrosion resistance in supercritical water. So, for example, in this graph, you can see the results of FQT test, where we have on the right side result of milled surface finish surface, and on left side polished surface finish surface. Clear differences on corrosion rate, beneficial effect of surface finish. But we don't have. We usually use this kind of simplified methods like a milling or grounding compared to polishing. But we need to focus more on the methods which are well defined. We should use the experience, for example, of Merctos project, where more methods were used, more very well defined methods for surface finish used. And we should test these methods, and we should find optimal method for surface finish of the future cladding, not only cladding material. If we look at another challenge or gap, this is the effect of pressure. We know that again, the higher the pressure, the higher the corrosion rate. It's pretty simple. We can see it on the left side. We can also see on the right side the same results for SCC, susceptibility. Again, the higher the pressure, the higher the susceptibility to SCC, the lower is the maximum stress at which the specimen broke. But we are doing it from two reasons. We need to optimize the pressure for the future ECC smart concept, for example, small modular reactor concept or HPLWR concept. And maybe 25 megapascal is not the best pressure we chose. Maybe we can go even a little bit lower pressure. And if we, for example, would reach some other more beneficial effect on corrosion resistance. Another reason why we should consider the pressure is that we have many results from different tests in superheated steam, which I already mentioned. And there are attempts to actually use this kind of superheated steam as a surrogate. That means this is a big thing, because if we want to simulate effects like flow rate, and if we want to affect like heat transfer, this kind of thing, we need pretty much robust facilities. And of course, using supercritical water, it's raising capital cost really very high. And then if we could use the surrogate like superheated steam at much lower pressure, it would save a lot of capital cost for us and make our life much easier. If we want to talk about the differences in the environment, what is the difference in steam and supercritical water? So we know that subcritical water, the corrosion is pure electrochemical process. When moving across the critical point, it's a kind of mixture of electrochemical and chemical oxidation. And moving farther to supercritical water, it's changing more or less into chemical oxidation. So when we see in the upper part of the plot, we have at the beginning mainly electrochemical process, and then at higher temperature of supercritical water, mostly chemical oxidation. If we go along the fuel cladding surface, we can see that we don't have isothermal situation. We have pressure, we have temperature development, as you can see in this red curve. And this is another effect we need to study, because most of the tests we have been doing are isothermal tests. We are testing coupons at one temperature, at one environmental conditions. But this is very far from the real case. In the real case, the temperature ranging from 300 up to 600, even 700 degrees C. So we have dynamic thermal situation, heat transfer along the fuel cladding, and we need to know what is the consequence for corrosion or SCC. There are very limited number of studies on this topic. One of them is actually in this graph on the right side. We don't see any big effect of heat transfer in this case. Even maybe we see that in isothermal conditions, corrosion rates are a little bit higher. But anyway, this needs to be tested, and again, we need to prepare dedicated experimental facilities for it. If you look at we talk about the flow rate, so that's one of the few studies on the left side. Flow rate effect clearly demonstrated many times that having a big effect on corrosion rate, and we need to make dedicated tests to find out. Another challenge or big gap is stress corrosion cracking testing. Because so far, most of the stress corrosion cracking experiments in supercritical water were limited to SSRT or constant extension rate tests. These tests are very useful, that's for sure, because it helps us to select materials quite fast. It helps us also to quantify certain change of conditions, but we are not getting any quantitative information, only very limited one. And that's why we need to go to more sophisticated crack growth rate, fracture mechanics based test, or SCC initiation test. One example of usefulness of SSRT test is alloy 800H tested on SCC susceptibility at different temperatures, and we can see the degrees of yield strength, mechanical properties due to temperature. The alloy showed low susceptibility to SCC in super and subcritical water. But what is very important for us is the change of mechanical properties. We can see big degrees in yield strength, maximum stress, and also in ductility, not so much in ductility, but definitely in these. So the discussion is to what extent, because we are using data from mechanical tests at temperatures, usually in air or in inert environment, but how relevant these data are when the components are actually exposed to real environmental condition of supercritical water. This needs to be answered, and I'm even in this area, we can have a look, and we need to compare to data, to mechanical test in air, and do the same test in the environment. If you look at the mechanism, so from SSRT test, we can never ever get any information about the mechanism of SCC. This mechanism will be much more complex in subcritical water, starting at low temperature supercritical water with probably electrochemical dissolution, which is well known. In fact, almost the same situation like we know from subcritical, from current light water reactors. And with the rising temperature, we will have more void diffusion and segregation and creep crack growth. As you can see in this example, we have intergranular growth of the crack, and then we can see that in front of the crack tip, we have already coalescence of voids, which later on connect and they move the crack farther. So originally, we have the initiation, maybe due to dissolution, electrochemistry, whatever, but then the crack growth is changing a little bit from SCC to creep. So the mechanism is actually joined, creep and SCC. If we look at what we are getting from this type of test, I would like then the crack growth rate, it will help us to define what is the stress effect on SCC. What is the maximum stress intensity factor for crack arrest? So, and then of course we can create so-called disposition lines. That means the dependency of crack growth rate based on stress and on all various conditions in the core, even related to chemistry or materials. And of course we need to focus on crack initiation test, because initiation is big part of the whole process. The propagation only smaller part. So we need to have a look at that and to find from the precursor and up to the growth of short tracks, and we have to have a look at it. There are only a few examples so far on fracture mechanics based crack growth rate test. On the right side is one of the oldest studies where they expose 1/2 CT specimen constantly loaded. In order to understand the whole thing, this crack growth rate is performed in several steps. At the beginning, we are pre-fatiguing crack using high amplitude, high frequency, and then we are slowly decreasing of load, and then we are slowly decreasing frequency and amplitude up to switch to constant load or constant stress situation. And there we start measuring 1,000, 2,000 hours real crack growth due to corrosion, stress corrosion cracking. We are using online monitoring system to get the crack growth. We are using direct current potential drop technique, and we are measuring crack growth in situ depending on load. And here you can see the results, and this is very interesting study because according to the study results of this study, you can see the black dots. That means the crack growth rates are reducing when we are crossing subcritical to supercritical water. Even at 500 degrees C kind of saturation, even it could go even lower. So in this case, it would mean that actually supercritical water is less detrimental, in fact, for stress corrosion cracking. But then we have another study on the left side, and then these guys, they measured the exact opposite. They measured higher crack growth rate with higher temperature of supercritical water, and even not depending on the composition of the V-mountain. So we definitely don't have enough information here. There is also other aspect of that, and that this is the study of Le Fou Zhang from Shanghai Yatong, one of the last, where he actually performed the test at 500 degrees C supercritical water, and then he was measuring 3.7 10 to minus 7 millimeters per second crack growth, and then he changed conditions after 1,000 hours that he changed media to argon atmosphere, and he measured 2 times slower crack growth, but still he measured the growth, and that means the SCC mechanism changed during the test and changing the conditions of this test to creep. So we can also expect at these temperatures, at such high temperatures, and for this material effect of creep. So in any case, this is the big gap in our research, and we need much more experimental result to actually get enough data and to evaluate this. Of course, effect of irradiation, that's really a huge challenge because so far we haven't performed any impile test. We have limited number of studies on irradiation effect on crack propagation. Here you can see the results, one of these studies, real effect of higher DPA on maximum crack depths, which was the criteria used in these SSRT tests. And if you look at the micrographs in the lower part, you can see huge growth of density of these cracks based on DPA, materials DPA. But here it's a huge gap. We haven't performed enough studies. I could mention ECC SMART project that we will evaluate irradiation effect at least from the corrosion point of view. But we need to perform the same study also for irradiation assisted stress corrosion cracking evaluation. If I look at the design challenge, and this is the last one, that's water chemistry. And water chemistry, I already mentioned that there are big changes in chemical properties due to cross to critical point. Of course, we have big problem with water radiolysis because we are expecting that it could be markedly different from that experience we have from lighter water reactors. So we need to perform dedicated tests. We need to do a lot of modeling on it. We need to understand, and we need to understand if we can extrapolate also behavior from light water reactors. And we expect, based on the results of radiolysis, we will see how strong effect it will have on corrosion and stress corrosion cracking. And of course, it can be reflected and follow-up testing if we see that there are some big changes, for example, in concentration of oxygens, we could expect. And of course, we need to establish a water chemistry control strategy. Of course, in this case, we can use the experience from current light water reactors, or supercritical boilers, and it should help us to simplify the whole process. And here experience is really huge. Okay, and now this is actually my last slide, and it's about the future plan, but it's not really future plans. It's a little bit past, present, and future, because ECC SMART as a natural development of supercritical water-cooled reactor towards small modular reactor technology started in 2019. So at the moment, so this is the past, and at the moment we are in the middle of experimental program, many tests running, and the project will finish in 2024. We have extensive material program where we are testing actually longer exposure times. We are focusing also on testing the real geometries of the fuel cladding in stress corrosion cracking testing. Radiolysis studies are planned within the project, and okay, I personally hope that this is just a start, and this is just a start for nice future with SCWR's SMR concept. Thank you very much.
Okay, thank you, Radek. Thanks a lot for a nice presentation. It was very complex, covering all or many challenges of the material degradation in supercritical water, very clearly explained. Thank you. I hope that maybe there is somebody who will ask some more question. No. All colleagues seems to be shy. So if you look, I will ask some tricky question because we have some moment for discussion. If you see on the line on the timeline different Gen 4 reactors. Do you still see like supercritical water reactor close to be applied and used soon? Because the water LVR and supercritical water, one can say similar medium, but as you explained, different. So what do you think where it would be between those generation 4 advanced reactors? What would be the time of deployment?
Well, first of all, you know, in Europe, a CWI is not considered as Gen 4 reactor. It's actually an evolutionary concept of light water reactors. So that's why it's in Eugenia and not in ESNI. So I believe that, okay, I believe in our philosophy. And our philosophy is a little bit, you know, improving things step by step. In last, I don't know, months, we are busy with kind of new roadmap for a CWR, and then we actually decided to go a little bit this way, to go step by step, first with increase of pressure, then increase of temperature, so more kind of evolutionary approach than target we will Gen 4 reactor in 20 years, and I think it's not really it's not really real. Yeah. I hope you like my answer.
Yeah. So thank you very much. Yes, working on another concept, I can imagine that it's pretty farther. So Radek already mentioned. Thank you, Radek. I think we can applaud to our guests. Of course, we will be happy if you stay with us and you listen other presentation. And Radek already mentioned in his presentation Project Meactos and also how important the surface treatment is for the material degradation in water or in supercritical water. And that's actually bridged to next presentation, which will be also sent from somewhere outside. This will be Maria Zimina, who will present us results or some of the results of the Meactos project. So Maria, I see you are online. Welcome and hello, and please, you can present.
Hello. I hope you are having a good time there. Can you hear me and can you see my screen?
Yes.
Okay. Yeah, this one, right? Can you confirm?
Perfect. Yep. It's in presentation
Thank you.
So you can start.
Okay, thank you very much. It's a pleasure to be with you, at least online today. So I would love to present the effect of surface treatment on environmental assisted crack initiation threshold of cold work type 316L stainless steel in light water reactor environments. It is a part of the collaborative project called Meactos, and I'll describe a bit of this later. And yes, as you can see, there were a lot of participating parties in this project. So this project is now finished. So what is MIACTUS is, it stands for the Mitigating Environmental Assisted Cracking through Optimization of Surface Conditions. And the main objective of the project was to improve the safety and the reliability of Gen 2 and 3 nuclear power plants by improving the resistance of those critical locations in the nuclear reactors, such as welds, and they are susceptible to environmental assisted cracking. And how we want to improve it is through the application of some kind of optimized surface machining and improving surface conditions. So the concept we've chosen as a consortium was that we quantify the susceptibility to stress corrosion cracking using accelerated testing methods such as constant extension rate tensile tests and constant load testing, use tapered specimens. So as I mentioned, this project started in 2017 and it's already finished in February 2022. So yeah, there were 16 partners from 12 European countries, including UK, which is not part of Europe anymore officially. And yeah, it was a very nice collaborative effort from all of us. So this project consisted of two parts. Two main parts. First was devoted to the nickel-based alloys, and the second one was stainless steel, particularly 316L cold work stainless steel. And today I will be focusing on this material. So the material was specifically manufactured to our goals, to fulfill our goals, and it was cold rolled stainless steel. It was a 13% cold work. So as you can see, the first step was the cold rolling. Then this panel was cut into the strips, which were further machined using different techniques, which I will be talking about later. And then after machining, the specimen for stress corrosion cracking testing were manufactured using EDM, and then we were happily we had all the samples distributed to the partners for the testing. So we used two types of specimens. One is FTT, which is a flat tapered specimen, which has a tapered gauge section here, which allows us to have more levels of stress during the test. And these specimens were machined in different ways. So we have 4 different surface treatments. First one is a RS, which is a reference surface, which was just ground using grid paper, silicon grid paper, and the other 3 were actually machining. STI stands for the standard industrial machining, which was chosen to compare the results to the actual industrial conditions. The second one was the SAM, which stands for Surface Advanced Machining 1 and 2. And the difference between 1 and 2 is that first one was phased milled with supercritical CO2 cooling, and the second one was the same but using the lubrication. And the second type of specimen which was used for the initiation testing was a sand sample, which stands for single edge notch tensile specimen, and the surface of the notch here was prepared as a reference surface, again ground with a silicon carbide paper. So testing conditions for the for this program were chosen as follows. So first task was accelerated testing for screening the conditions for the further stress corrosion initiation testing. So we used the FTT specimens with tapered specimens, and we performed accelerated constant extension rate tensile testing with different nominal strain rates, and in two different water environments, BWR and PWR. So according to this, after this test, we identified the position of the last crack, which has to be more than 20 microns in length and straight and perpendicular to the load direction. So it was determined by SEM analysis. Then we assessed the cross section and determined the characteristic critical stress for each surface, finish, and for each strain rate. And then using this data, the stress threshold was obtained by extrapolation of this characteristic critical stress to 0 nominal strain rate. And that's how we by obtaining this stress threshold, we were able to set the parameters to the second task, which was the verification task using constant load tensile testing for this crack initiation testing. In this part, we used both FTT and SENS specimen. We used constant load in testing for thousands of hours, or some of the tests were further extended to until cracks were observed, because we didn't observe cracks after thousands of hours in some cases. The same environments were chosen, BWR and PWR. Also, I probably need to mention why we used two environments, obviously because we wanted oxidizing and reducing conditions to be represented. Yeah, so the constant load testing for the FTT specimen was performed when the maximum stress was equal to the slow straining rate yield stress at the given temperature from the previous task. And for the SENS specimen, notched specimen, we had the applied stress in the notch, which was equal to the yield stress times 1.8, which was done to match the slow strain rate conditions. And the critical stress was also evaluated from tapered specimens in this task to increase the statistics. So the main point of this constant load tensile testing was the determination of the time to crack initiation, so initiation time. So the results showed that first we obviously characterized all the surface and subsurface characteristics of all four surface conditions, and we can see here clearly that in all cases we have ultrafine grain layer under the surface, and in all four cases we have either slightly deformed zone or heavily deformed zone underneath this UFG layer. And so obviously the thickness of this layer varies with different applied stress or deformation. And so we calculated the thicknesses of these layers, and you can see that for STI, for example, it's more than 3 microns, which corresponds to the standard, advanced machining 1, and but it is a bit thinner in SAM2, while when you just perform grinding on the surface, you end up with having just a small ultrafine grain layer, which is about half of a micron in thickness, and the material is almost not deformed underneath. We still need to remember that this material is 13% cold work, so this amount of deformation here is induced during the processing or manufacturing. We also measured the residual stresses of all four materials, and we found that there is a tensile residual stresses in all the machined specimens, but not in the ground one, where, as I said, the structure is a bit different. After the first task, after the screening, using this accelerated testing, we observed intergranular or mixed cracking in all cases, in both two environments, and for all four surface treatments. In case of task 2, initiation testing, we observed the same situation with a bit different structure of the cracks, but still intergranular or mixed. And we, as Radek mentioned today, we can't really talk about the mechanism of this cracking using this accelerated testing without performing the crack growth tests. However, if we look at the BWI environment, which is oxidizing environment at 288 centigrades, we can see that these calculated critical stress values are similar for all surface treatments, and with those two advanced machining procedures which were proposed, they perform similar to the standard machining used in the power plants and the reference surface finishes. Yeah, all values were found to be close to the slow strain rate, yield strength level, and the crack concentration, which was calculated using SEM, also was followed this rule that the highest crack concentration was observed in SEM1 and less in SEM2, less in STI, and then reference surface, which suspiciously follows the size of the ultrafine grain layer. And we think that in BWI environment, where the oxidation is more intense than in, for example, PW water, it can be explained by the oxidizing conditions. So if we look at the PWI environment results, we also see the similar tendency as in BWR, so the critical stress values are also similar and are irrespective to the surface treatment. We also found that the plastic strain contributing to environmental assistant cracking initiation was less than 0.5%, and the crack concentration was similar for STI, SAM1 and RS surface, and there were no cracks on advanced machining second with the lubricant. So so we know that the cold work 316 shows very low susceptibility to EAC, and we and the higher critical stresses means the lower SEC initiation susceptibility. For the constant load tests using flat tapered tensile specimen and notched specimen sent, we detected only few cracks after the initial test period of 1,000 hours, and as I mentioned already, not on every specimen. So some tests were performed for longer time, up to 2,100 hours, and the average critical stress from this constant load test was always lower than the critical stress from CERT testing. And the reason why is it so? It is because the CERT testing is an accelerated testing, and it introduces high plastic strain into the EAS initiation process. That's why those values differ. And critical stress determined from constant load tests with tapered specimen was not dependent on time to crack initiation. The time to the initiation was significantly reduced when the notch effect was inserted, which is quite interesting finding. And EAC initiation was slower in oxidizing environment and BWR compared to the reducing environment. So to conclude what I've really briefly tried to present here, we have tested the 4 different surface treatments and the effect of the surface treatments on the initiation behavior of cold work 316 Hal stainless steel in 2 environments, in BWR and PWR. And we used accelerated constant extension rate tests, tensile tests. After that, we acquired this threshold stresses values, and we performed constant load testing, initiation testing, and then we realized that there is no significant effect on the various surface treatments on the EAC characteristics, and but we also found that the crack concentration is different in different environments, and in BWR, normal water chemistry, it follows the same trend as the ultrafine grain thickness, ultrafine grain layer thickness, and in PWR, it doesn't. In oxygenated BWR condition, a thicker oxide layer was built on the surface, and it delays the oxidation of the grain boundaries and slip bands when compared to the reducing PWR conditions. That is why probably the constant load testing, the resulting time to initiation data in simulated PWR conditions were longer than the ones observed in the reducing PWR environments. Critical stress determined from constant load testing with tapered specimens was not dependent on time to crack initiation, and the time to crack initiation was significantly reduced when the notch effect was inserted. There were the testing results, and I would like also to mention the general conclusion which we observed during the whole project. So for the 316L with the applied cold work lever, which is 13% in our case, there is clear no benefit in the applied surface treatment. However, this material is always resistant to AAC initiation, so the initial degree of cold work applied may not have been sufficient to increase the susceptibility to AAC, although we couldn't introduce more cold work because we wanted to simulate the real conditions in the power plants, and this is the first point. The other point is that the advanced machining techniques, they seem to have a similar or even slightly positive impact on EAC initiation compared to the standard industrial method. But those methods have other benefits, like, for example, higher cutting speed and less pollution by lubricants. So it is good to investigate those advanced manufacturing methods further, and it is very promising and might be used as an alternative to the standard procedures. And the significant results, I think, is that the constant extension rate test revealed that this testing of tapered specimens can be really successfully used for the screening of the EAC initiation's acceptability. And with that, I will thank you for your attention. And I hope you heard me well.
Thank you, Maria. Thank you for your presentation. I will look if there is some question in audience. Still no one there. Yeah, there is. Okay, thank you, Monica.
Hi, Monica.
Hi, Masha. Nice presentation, thank you. And just a question, did you measure the surface roughness when you treated the surface by different methods?
Yeah.
I don't know, maybe you show this information.
No, I didn't show it yet, but we measured surface roughness and micro hardness and nano hardness. So we compared the initial state of the, I can't tell you the numbers, but yeah, I can look them up, definitely.
Okay, at least the method, if you use contact measurement or optical one?
Yeah, the different partners used the different methods. For example, even in CVR, we used in Pilsen this profilometer for the notch. So that's one of the methods. Then for the tapered flat specimens, we use just a normal, like, roughness meter. So like the contact one. And yes, I'm not sure, but I think different partners used also laser and optical ones. Yeah.
And do you observe some bigger differences between these two methods? Or how big? You don't know. You don't remember the number.
Yeah, there was a whole task for the pre-characterization, obviously. But if I maybe can show you the so here, if you the other one. Okay, I'll leave it like this. But you can see that the surface is quite rough for the machined specimens.
Yes, sure.
Yeah.
The question was the differences between the different method of the measurement. I mean, in case you use contact and non-contact, so just
I'm not aware of this. Yeah,
okay.
But we can look it up in the report. It's quite easy.
Perfect. I will contact you.
Okay.
Thank you.
No problem.
So, is there any other question? No, it seems no. So, thank you, Maria. Thank you for a nice presentation and being with us and all the work that you have been doing for CVR. Okay. It was nice to see at least like this. Thank you.
Same.
So,
thank you. Take care.
And now I would like to invite our colleague in person. His name is Lukáš Košek, and I will tell you.
Okay. Hello, everybody. I'm Lukáš Košek, and I will talk about structural materials for lead-fast cooled reactor. I have lots of slides, so I should be efficient. So let's go to the reactor. It's a pool type reactor. All liquid metal cooled reactors are pool type. All components are inserted into the reactor from the top. So there is a steam generator with pumps integrated in one unit. There is a core, and I will talk today mainly about P16L, that is supposed to be a reactor vessel, and 1515 titanium or 9% chromium steels, ferritic martensitic, as candidates for fuel cladding. This cladding has thickness of the wall 0.4 millimeters, so its corrosion is very critical. These reactors are very compact. They have high power density. They are low pressure designs. Military loves them because they produce the plutonium and have very high burn-up. So these are very perfect, and we don't use them because of materials problem. This is overview of those materials. It's stainless steel 316L, low carbon and nitrogen controlled to avoid the aging effects. It's dedicated for main vessel and some inner components. 1515 titanium. It was developed for sodium cooled reactors as cladding material that have no problems with swelling. And grain 91 is 9% chromium, 1% molybdenum steel that is supposed to be perfect cladding, but it has some corrosion issues, and it has the best resistance to swelling. It resists very high dPa. So problem with this coolants is in let's say mass transfer corrosion. It's a bit different corrosion. It's inherent to all a non-isothermal system. It's based on solubility of steel elements in circulating metal, and you will develop, dissolve some of your reactor in core and transfer it to cold leg. And that's the main problem of this system. You can see here one example of, let's say, low carbon steel at very high temperature. It takes 400 hours to plug with iron, but if you put there some stainless steel with containing nickel, then you can plug it very fast. So the main factors are temperature and solubility of these elements, and flow rate, of course, because there is a boundary between metal and flowing coolant near the wall, that its thickness control the diffusion processes and speed of your dissolution. There is a comparison of different coolants. For example, the sodium was used in past because there is no corrosion of stainless steel because of very low solubility of steel elements in it. On opposite side, there is lead bismuth eutectic alloy that has very high solubility of nickel. You can see there is 1 million of ppm or something like that. That means that there is a problem that this mass transfer. And in lead, this situation, let's say, is 1 order of magnitude better. So the corrosion rate depends on solubility of element, the difference between hot leg and cold leg, and flow velocity, and also there is very important presence of non-metallic elements that can speed up or slow down the corrosion process. So what we can do with this corrosion, the simplest idea is to grow diffusion barrier, that is oxide, and slow down this dissolution process. It was demonstrated by Russians on their submarines that they find out that if you put a small amount of oxygen, 5 to minus 8% of oxygen, you will develop this spinel iron chromium based that significantly slow down corrosion process. So there are several mitigation strategies for this corrosion. One of them, and it's available now, is this oxidation or growing up this oxide layer that has some advantages. That is simple, but the problem is that it's kind of balance between oxidation, dissolution, and it works to certain temperature, let's say 400, 500 maximum. Then some short-term solution can be applied a coating on the internal reactor surfaces, but as all coating, there is a problem with what you will do with the defect in the coating. So when there is a defect, you then have to rely on your oxygen control strategy, and that may develop some localized issue that are not critical for a reactor vessel, but there may be a problem for cladding because it's a very thin tube. And the ultimate solution is to have a material that is resistant. So you can reach it by addition of silicon to ferritic Martensburg steels. That is the Russian way. It can be successful, but it has some impact on mechanical properties. European way is add the alumina or aluminum to austenite to get this material. Problem is that qualification of this material is very long, and it requires some creep testing, and that's why I think that some demonstrator will be based on oxygen strategy with some coatings. This diagram shows you stability of oxides, and we are limited with this oxygen dosing from top by solubility of lead oxides. And also from bottom side, we are limited by dissolution of these iron oxides that are protecting our structures. You can also see here, if you go down with oxygen, that's in down the direction, there is a stability of silicon oxide or alumina oxide, so they will sustain very low oxygen concentrations at very high temperatures, and that's why they were chosen as coatings or the addition to this special alloys that are resistant to this media. Another fact is visible on this chart, that there is a problem if you increase the efficiency by increasing the outlet temperature. You closing this window that's now pretty narrow. That means that it puts some stress on your oxygen control system. So that was some kind of brief introduction into chemistry of liquid metal cooled reactors. 3 years ago, we were preparing some long-term experiment and built austenitic loop for that. And I was expecting that we will have some kind of dissolution contest between our loop and the specimens. You can see here that in literature at relatively high temperature, 500 degrees C, even with oxygen dosing, they experienced very large dissolution attack. It was LBE after 2000 hours, and there is a damage like 1 millimeter big. So that was our expectation. Our goal was test some reference materials from RCC and RX code that were mentioned they were chosen for Alfred reactor for thick-walled components. And it was 316L and 316L low nitrogen and submerged arc weld and TIG welds, and also 1515 titanium that was 20% cold work and was experimentally made, and we also tested grade 91. So these are the material in S-receive state. 316L was solution annealed. 1515 titanium, you can see some slip bands from cold working and big grains. There is titanium nitride and ferritic martensitic structure of this steel. So our specimens were cut from the plates by electric discharge, and the surface was finished by machining that creates a very fine modified layer on the surface that was that became pretty important in our corrosion results. It was about 3 microns thick. You can see also some damage by machining. It's about 100 micrometers deep. So this is our specimens. We place them into corrosion loop that has, it's non-isothermal. It has a hot leg, cold leg with cooled filter. In hot leg, there is a mass exchanger to allow us to control oxygen content. There are 2 parallel corrosion sections where specimens were placed in a manner that's shown on this picture. And there is 4 oxygen sensors. One at the inlet and outlet of the mass exchanger, one in hot leg tube, and one is cold leg tube. So there is a record of this 20,000 hour-long experiment. Most important is the record of the oxygen sensors. There are 4 of them, and you can see that every 1,000 hours there was some peak of oxygen that was indicating our replacement of the specimens. In one leg, there was long-term specimens for 8,000 and 16,000 hours, and in another leg, there was short-term exposed specimens that were frequently replaced. So you can see it's a bit complex matrix. Here is also a record of temperature, it's 480 degrees C. There is also a record of flow rates in each leg and a record of temperature in cold leg. So evaluation of specimens was done on metallographic cross-section. We fit the diameter circle on the metallographic transverse cross-section, and also do some characterization in systematic way around the perimeter of the specimen to calculate the thickness of the features that were on the perimeter. So the result is here. There is a comparison of ferritic steels. We also tested the Eurofer, I didn't mention, for just our interest, and there is stainless steel. You can see here that austenitic steel has virtually no corrosion damage except this 4,000 old specimens. Ferritic martensitic steel exhibits some, let's say, uniform oxidation that gradually increased in time, with exception this 8,000 old grade 91 specimens. You can notice here that the corrosion of ferritic steels are much higher, the material loss. This is comparison of welds with base material. You can see there is no difference between the welds and 316L base material. So let's go back to kinetics of stainless ferritic martensitic steel. If this corrosion process is diffusion control, that is what we want, we can fit the kinetics by parabolic curve. That's possible for T91, but it's not possible to do that for Eurofer because it's gradually losing the oxide. The exceptional specimen was 8,000 old because it doesn't develop the outer magnetite oxide. That was very interesting, and it's still not very clear why it's not happening, but it's a combination of surface state and some environmental factors like non-frequent replacement of this particular specimen. If we look on typical corrosion layer, we can see it's same for all ferritic materials, and it's similar to what you see in water and other environments. It will develop a duplex scale that consists of outer oxide that is magnetic, or it's iron-rich spinel that's formed by diffusion of iron from this inner oxide outside and oxidized from the top, so this is a large grain. Very fine inner oxide that has very fixed ratio dependent on environment, on type of ferritic steel, on time of exposure, and there is only difference between the grain 91 and Eurofer that there is slightly increasing the chromium towards the metal and oxide interface. There is also what we call internal oxidation zone, that zone that contains 20% atomic of oxygen and go deep into the material. In Eurofer, this zone is extremely large. Here is a fit of each sublayer, or like same kinetics like before. And you can see that only grain 91 spinel layer follows this parabolic curve. So it means that it breaks down by diffusion, this corrosion process. I would not say that I can fit this model into the total oxide thickness. You can see here it doesn't follow it. Unless I introduce the integration constant, then it's highly questionable how to explain this model. And it's on par what we can get on same temperature in water, like this constant, basically. So the difference between Eurofer and grade 91, both are 9% chromium steels, they should behave similar, is by formation of this very thin layer on between the spinel internal oxidation zone interface. That's Eurofer is unable to form. The explanation I don't have. So the summary, the spinel is probably responsible for this corrosion resistance. Both steels exhibit high temperature oxidation. You can see that Eurofer has very large internal oxidation zone. Back to the austenitic steel that are more interesting. Why we have this highest corrosion rate of 4,000 ton specimens was quite a mystery. We're talking about those two specimens. You can see that at the initial short exposure, all austenitic steels are have very thin oxide, it's blue, and then became thicker. And this black color indicates there is a formation of outer oxide similar to the ferritic martensitic steel. And we have same oxidation rate, and this particular specimen looks intact. So fact is that we run into the difficulties to measure actually this corrosion rate, because this specimen was made by a different guy operating the machining, and he makes it very raw, and this rawness is around this corrosion loss. So general corrosion process of austenitic steel is formation of extremely thin layer, not much more than 100, 200, 300. That exfoliate and regenerate, and it can be present here even after 16,000 hours, or it may fail and then some lead penetration occurs or localized oxidation. We try to identify what's the composition of this very thin layer that is few, let's say 100 nanometers. It's really hard to do it. So we combine the XRD with TM to eliminate the amount of phases. And we figure out it's very interesting spinel phase that has some kind of dynamics over the time of exposure. Initial higher content of chromium is reflected by higher content of in 316 by higher content of chromium in the spinel phase. In 1515 titanium is only 15% of chromium, so there is at the beginning 19% of chromium in the spinel and then decreases, and iron is replaced by manganese. Quite interesting. This is the structural, the phase we identify there. It can be there even after 20,000 hours. So it prevents from solution-based attack, slows down oxidation, and may of course fail as soon as 1,000 hours. Detailed look on this spinel on TEM reveals that there is growing, this fine grain layer is what was made by the machining, and the new phases are precipitated there with ferritic phase. It's quite interesting. That has this composition, regardless the material. And after 16,000 hours, this depleted layer became few micrometers thick, and new phases are precipitated here. The nickel is concentrated in FCC phase, and there is depleted DCC phase accompanied with something that contains a very large amount of chromium. That's similar, something like spinodal decomposition of delta ferrite in duplex steel, but we have austenitic steel. It's quite interesting problem. That may affect some long-term behavior, but 16,000 hours is not enough. So there are some localized issues that are connected with depletion of this fine grain layer created by machining. When this corrosion or oxidation gets through, we have accelerated oxidation that is connected with outer iron oxide formation that's similar to ferritic martensitic steel. The weld behavior is very similar, like normal base material. It's protected by very thin oxide layer. There is depletion layer underneath with this nickel-rich FCC and iron-rich BCC phases with some localized deep oxidation. That looks like that. You can see here that there is a nickel concentrated around this. This chromium is here, and these green spots are nickel-rich alloys. Let's make it open the path probably for a localized nickel dissolution, because nickel is highly soluble in the liquid metal. We try removing this fine grain layer from machining by electropolishing, and what we get here is immediate attack in between the grains by lead. After 18,000 hours, you can see in the nickel phase the dissolution happens. So it's maybe the mechanism how in long term this large-scale dissolution attack develops. But because the solubility of nickel is 1 order of magnitude lower than lead bismuth, we have not that severe problem like I demonstrated on the first slide there. We also did some analysis of coolant during the exposure, and the main point is here that there is no large-scale dissolution attack in the loop. The nickel is supposed to be most abundant corrosion product because we have stainless steel, we have stainless steel specimens, stainless steel loop. It's the majority of wetted surface is containing nickel, and nickel is not there. So, in filter content we have found there is lots of iron, but no nickel. Iron is not oxidized, it's a big surprise to us, and I think it's maybe affecting this free iron, the signal of oxygen sensors, and may be the reason that we are having in the loop lower content of oxygen that we are measuring, and therefore there is a concentration of nickel in the surface of our spinning layers. So to conclude this, we have no large-scale nickel leaching. That's the key message. The second important thing is surface fine-grained water hardened layer created this nice corrosion resistance against the dissolution. Oxide layer are damaged by thermal cycling during specimens replacement because they crack and then develop some localized. And that chromium, 9% chromium steel are suffering from high temperature oxidation at a higher rate than stainless steel. Okay.
Okay, thanks. I thank to Lukáš for his presentation. You could see that there is a lot of work, a lot of samples, a lot of hours of experiments, but also hours of sitting with the microscope and looking into the structure and trying to understand the mechanism. It's yeah, extensive and great work. Do you have any question? Seems that everyone understood what you were saying. It was clear and very nice presentation. Thank you very much. And now, if you are looking forward to lunch, no lunch, but the next presentation related to degradation of material in high temperature helium, I have to disappoint you. We have small change in our program, but I would like to offer you a very nice presentation, which is dealing with the cold spray technology in nuclear application, which should be the last, so it will be now, and then we will swap our presentation about materials in helium to the end. So you are forced in this way to stay here until the end. Okay.
Good. Before lunch, I will speak in my presentation about our experience with cold spray technology. In my presentation, I will provide information about research and development projects. Then I will speak about research in the area of cold spray coating properties, about mechanical properties, then about assessment of components repelled by cold spraying from the outside, about potentiometric analysis, about fatigue tests of cold spray coatings, and about inspectability of components with cold spray coatings. And at the end I will provide some information about possible applications, about usage of cold spray coatings as a protection of dissimilar metal worlds against stress corrosion cracking, and about repairs of sealing surfaces by cold spray coatings, and then I will make some conclusions. All activities were done under project of Technology Agency of the Czech Republic within the National Center of Competence Program. First project started in 2019 till 2020. The second one in 2021, and this year we have the last project. The main outputs for the application of cold spray technology to substrates made of materials used at VVR 440 and VVR 1000 nuclear power plants. We were using nickel chrome and nickel powders of different particle sizes, and also once we used helium as a tracking gas, but the rest applications was done by using dusíkys nitrogen. So let me first speak about mechanical properties of cold spray coatings. We performed these tests at room temperature and at the temperature of 350 degrees of centigrade. As a substrates, we used so-called Ochnot and then 22K ferritioperitic steel. We used steel tubes of different thicknesses and diameters to produce test samples. The orientation of the samples was in the longitudinal direction, axial direction of the tubes. So first we perform tests to get mechanical properties. I should also mention that these tests were done only for nickel chrome powder with a particle size of 15 to 32 micrometers. So first we perform tensile tests of the substrates. For comparison, we used rod samples and then also tube flat samples. Tube flat samples you can figure you can see on the right up. And then we perform tensile tests of the cold spray coating itself. In this case, we had flat samples, and the last measurements were done for substrates with cold spray coating, and in this case, we used tube flat samples. The results are on this slide. What concerns of rod samples, we perform measurement at room temperature and temperature of 350 degrees of centigrade. Here are results of substrates. Then we compare these results with results with using tube flats. These were done only for room temperature, and we can say that we receive similar results from rod samples and tube flat samples. Here you can see results of cold spray material itself. Let's say there is 0, the yield strength is has the same value as ultimate strength. And if we perform tests to get mechanical properties of substrates with cold spray, here you can see that the ultimate strength dropped, and I will speak about usage of these results later. What we also perform, we try to improve properties by heat treatment. The first type was to go to temperature of 640 degrees of centigrade. It was in the first project. In the second project, we went to temperature 390 degrees of centigrade, but the time of heat treatment was 120 hours. The result of what we get after heat treatment is that we can a little bit improve strain of 0.2%. So it helped a little bit, but not in the way which was expected. What concerns of porosity of cold spray? Cold spray has very low porosity in comparison with other hot sprays. Porosity is 0.1814. This is for when we use this substrate and tracking medium nitrogen. With helium we receive lower porosities. So conclusions are following. The ultimate tensile strength limit is like the strength limits of the tested substrates. So the results are for cold spray material itself. The cold spray material is brittle, it has almost zero ductility, which can be improved by heat treatment. On the types of samples used, tube flat samples appear to be suitable for testing the substrate and cold spray pair in terms of sample geometry. The tensile test of the substrate cold spray pair can be used to evaluate whether the mechanical properties of the cold spray layer are satisfactory for supplementing the substrate material by cold spray coating for concrete tube component. Cold spray coatings show very low porosity in contrast to other hot sprays. It's good information from the point of view of inspectability. I will speak about it later. And finer powder particles or helium as a medium, it means then a lower porosity and higher tensile stresses. Then we tried and wanted to know information what is flowability of cold spray. So we wanted to evaluate the coating's ability to fill a defect in the substrate. We used tube pipes cut from technology in Temelin and PP. We made a V-groove and hose with diameters of 1, 2, and 3 millimeters. And then we applied cold spray to cover these artificial defects with minimum coating thickness of 1 millimeter. We also perform two types of coating. We had a nozzle perpendicular to the surface, and then the second type of coating was alternately at two angles, plus 45 and minus 45 degrees. For one test pipe, we put aluminum plugs into hose with diameters of 2 and 3 millimeters before making cold spray coating. And then we perform metallographical cuttings and light microscopy. Results are here. We can say then if we use nozzle perpendicular to the surface of the pipe, only non-passable V-groove was filled. The other through grooves were not filled. You can see that here. When we performed spraying with gaskets for 2 and 3 millimeter diameter notches, we could see good results, but then it's a question of corrosion resistance of this. And the best results were when we were spraying with a nozzle at angles plus 45 degrees and minus 45 degrees, applied 3 times in total. We then received compact integral covering layer, which covered all the notches. The swollen layer also showed the least porosity. The disadvantage of this configuration is the lower penetration ability of spraying in depth of angle 45 degrees. You can see that here. This angle is 45 degrees. So it follows from the above that for specific applications it is necessary to carry out the test to optimize spraying. Other tests which were performed are potentiometric analysis of cold spray coating. A principle of measurement you can see on this figure. We are using 3 electrode system: graphite counter electrode, silver chloride reference electrode. The result is recording of the depends of the current on the potential of the sample with respect to the reference electrode. Potential dynamic curves were recorded for the tested materials, and at the same time the corrosion potential was determined in the environment of an aqueous solution of 58 ppm chloride sodium at room temperature. Conclusions from this analysis. Differences were found between coatings with different application angles. In the case we were using perpendicular and application at angle of 45 degrees. The coating applied at angle of 45 degrees had a lower corrosion potential and a greater dispersion in the shape of the curves. With consensus of substrates, the 22K steel used has a lower corrosion potential than both coatings, nickel chrome perpendicular 45. In the case of the second substrate, Ochnot steel, the corrosion potential is higher than 22K steel and both coatings. The corrosion potential values and the shapes of the recorded curves of both materials correspond to the expected behavior in the used environment. So according to the above mentioned, cold spray coatings should not reduce corrosion resistance of substrates materials. This year we perform fatigue tests of cold spray coatings. First we manufactured plate and sprayed it with nickel chrome and nickel powders. As a substrate we used steel 1.4541 with thickness of 16 millimeters, and then we cut this plate and we received 15 pieces of each. So in total we had 30 pieces of samples. And then we performed cyclic fatigue and thermal fatigue. What concerns of cyclic fatigue, we had 2 types of loads. After applying of fatigue, we performed UT, non-destructive testing, and microanalysis. What concerns of thermal fatigue, the first type was drastic. We heated samples up to 320 degrees of centigrade, followed by cooling with water to room temperature. We tried to perform 30 cycles. And because from the low cycle fatigue, we had not damaged samples, we made decision with chest to perform supplementary tests for thermal fatigue, which would correspond to the secondary site of nuclear power plant Temelín. And in this case, we performed 10 cycles. Here are results. For, let's say, Fmax 158 megapascal, none of 5 pieces had a fracture for both powders, nickel and nickel chrome. The second low type, in this case, we on one piece of sample, we optimize maximum stress for both powders. The optimized value was 400 megapascals, and you can see nickel chrome was good, no fractures after 100,000 cycles. With consent of nickel, one piece was without fracture, and three pieces had fracture with this number of cycles. Here is example of fracture after cyclic loading. What concerns of thermal fatigue, samples with nickel chrome powder showed visible peeling already after the first or 3 cycles. Nickel chrome coating was better. We optically observed peeling after 30 cycles. Then, as I mentioned, we performed supplementary tests. These tests, we heat samples to temperature 170 degrees, and then up to 270 degrees, and then cooled down these samples. And after 10 cycles, for both types of coating, no micro cracks were recorded. So we can say if operator will use cold spray coatings on secondary site of nuclear power plant, then these coatings should survive, let's say, 10 shutdowns of the plant. Now let me speak about inspectability of components with cold spray coating. We used pulse echo technique and phase array technique. Pulse echo was for measuring of the thickness and ultrasonic features of cold spray material. Phase array technique was used for detection defects and for sizing of defects. We manufactured these step gauges. Here is measurement of one step in this step gauge. And as I mentioned, these materials are good for inspections. Here is example of detectability and sizing of EDM notches. And again, it works like with samples of steel material. So conclusions there is not so much time. The main conclusion is that cold spray coatings can be inspected using pulse echo, ultrasonic testing, and phase array techniques, unlike other hot sprays. And now, two examples where we think cold spray could be used. Cold spray coatings could be used as a protection of the similar metal welds against stress corrosion cracking. We cooperated with Impact Company from Germany. Cold spray was deposited in the angle which can be achieved if we take into consideration the length of the tube. And in this first injection procedure, the results were not good what concerns of high porosity. So then we discussed with them how to improve it. We removed weld root, and we also improved laying of layers or spraying of layers. And the results are here. Yes, there is some porosity what concerns of nickel powder, but samples survived tests in salt fog, and we didn't see any attack on the substrate through the layer of cold spray coating. What concerns of porosity, nickel chrome is better than nickel powder, and the results again were very good after tests in salt fog. And the last example is this will be done in November now and December this year. We discussed with chess the usage of cold spray for repairs of sealing surfaces of flanges. On this picture you can see simulation of corrosion defect. Now we send this flange to Impact Innovation. In Impact they will apply cold spray to the whole part of sealing surface. Then the surface will be processed to create new sealing surface, and more tests will be done in UAM Institute in Brno. They performed flange leakage tests without any simulated defect, and after application of cold spray they will perform leakage tests of the repaired flange, and we will see the results from the point of view of leakage. And we in CVR, we will evaluate microstructure of cold spray coating and substrate interfaces in laboratories in Pilsen. So, short conclusion, cold spray is, let's say, not new technology, but in nuclear power plants application, it's new technology. We know that also EDF is performing some testing to use these technology. And there will be its greater usability after possibility of usage of mobile devices for cold spray spraying for in situ repairs in nuclear power plant technologies. As I have already mentioned, everything, all coatings were produced in Impact Innovation Company, and on these web pages you can find more information about this technology. Thank you for your attention.
I thank Jaroslav for a very interesting presentation about the coatings. as another way of improvement of the structural materials, not only for nuclear energy. Is any question here? It's on website, I haven't seen any. Somebody in auditorium? No.
It's time for lunch.
Yeah, that's true. It's time for lunch. So we thank you for your presentation. Thank you.